Okay, I'm gonna begin what I'm gonna call part two. Eventually, I'm gonna probably edit part one and put part two together, but I'm gonna do this one, kind of just get it done and out here because this whole idea about bringing deep ocean crude up by tankers is just a whole phenomenal thing. Copilot talked about it being a new era or whatever in deep ocean crude. I'm actually going to expand wildly on this whole idea here. I'm going to call this one here. I'm going to do. I'm going to call this episode the DOTC, the Deep Ocean Transportation Corporation Incorporated. The Angel Gabriel says, "Go see what the DOTC can do for you." I'm going to tell you, I'm freelance and I'm just gonna freelance this material. I've been through it enough, and I'm gonna make it very fast. I'm gonna probably miss things or forget things, but when I do an edit, we'll get back into this. I'm gonna move on real quick. I'm gonna point out that by the time this episode here ends, you're gonna begin to understand why I doubt anybody has really ever thought about using bladder tankers to bring deep ocean crude up from the ocean floor to begin with. And there's other aspects of this, and when I close this, you're going to see why this technology needs to be developed. It's something that hasn't really been done before. I'm going to start out first off. Let's talk about how they do deep ocean crude. All of this oil production at sea has always been connected by pipe. Back prior to even the 1900s, they were already offshore in California, and they were already running pipelines. Now, they expanded along the continental shelf. Now, I'm going to point out one thing about this tanker system. It's really not really economical. There's no real reason to use it in anything in the depths of the continental shelf. This is a deep ocean crude. Really, for this to be effective, I think the best depth would be to look at would be at 2,000 feet and deeper. I also want to point out that Copilot and I talk a lot about 6,000 feet because that's kind of a familiar territory for what they're doing in deep ocean, or what they call ultra deep water production. Okay. Copilot has told me that the actual operational bottom, or the operational floor of these tankers is actually 10,000 feet. This thing, some engineering concerns, but these tankers, this technology could be used to 10,000 feet with materials we already have. Okay, now this is where the bar rate starts to come in effect, because we all know bar rate means that materials, especially like synthetic materials, change properties when they're under extreme pressure. That's why bar rates matter. The idea of filling a tanker up, as long as you keep that pump and that tanker at the relatively same depth, you can use a low pressure pump to fill a balloon with. Now let me show you something. Let's get back here. We were on the coming out of the continental shelf. At the first, in somewhere around 1965, they started the first deep well, what they called the deep well. It was something like 1,000 feet. That was done in 1965. I like to point out that scuba divers can actually operate in 1,000 feet of water, and they actually have something that they call an open ocean scuba dive, some kind of open ocean technique where people can actually go all the way down to somewhere around close to 2,000 feet that you can actually dive to. But that's a very specialized technique here to go below that scuba depth. But I'm just pointing out that human beings can actually still be at these depths, and in like diver suits, or scuba works to 1,000 feet, but you can go deeper. I don't want to dwell on that too much. Much beyond that, below 2,000 feet, you're into robotics, remote operated vehicles. You can see as they've gone out, they've simply extended pipelines, you know, like they went to some of these rigid platforms where they sat on the floor. They were all done by pipelines. Now, and then you move out here to these ultra deep water production things, which they call the deep water era 2,000 to 5,000 feet. Ultra deep water is greater than 5,000 feet. So I'm just pointing out with the 6,000 feet that this thing's operational in the deep water, ultra deep water region of 5,000 feet, and actually all the way down to 10,000 feet. Okay. And that's going to become important later, especially when I demonstrate to you why I don't believe anybody's ever really put much thought into these tankers. Kind of funny because when I first came up with this idea, I was thinking of these tankers as something that we could control, you know, like an airplane or something, you know, that we could pump oil into these tankers and they could just do this ginger flight to some other remote terminal, be pumped down. And I was working with Copilot, and I didn't really understand. I've since then I've done a lot more work with Copilot, but I'm gonna demonstrate to you why. Number one, it's not really possible to give a tanker like this any horizontal direction anyway. Something I hadn't realized until I started asking Copilot some more questions. Copilot drew out this tanker thing with this monstrosity wings on it, okay, to give it any horizontal control at all. Now, here's the interesting thing. We're going to get into the reason why. I finally realized here, the first thing, and one thing that I asked Copilot here, I said, how fast, I was working with a 100,000 barrel tanker, okay? And I asked Copilot, I said, how fast would that 100,000 barrel tanker go if we released it at a depth of 6,000 feet? How long would it take it to surface? And Copilot came back with this answer, somewhere between 5 and 6 minutes. Okay, all right. We're lifting 100,000 barrels of oil over a mile in approximately 4 to 6 minutes with this 100,000 barrel tanker. I then decided to ask Copilot, okay, let's go to the 1,000,000 barrel tanker. All right, how fast does that 1,000,000 barrel tanker rise from a depth of 6,000 feet to sea level? Copilot came back with a calculation of between 1 and 2 minutes. And then I was like, wow. I began to realize something about horizontal control. You don't have the time for horizontal control. So I decided here, the next real question here then became just exactly how much buoyant force is on these tankers. In other words, while I'm filling these tankers up, I'm going to have to keep them moored, okay? To keep them moored, I'm going to have to keep them tied down to something that weighs more than the excess buoyant force, okay? Now, here's the interesting thing. This 1,000,000 barrel tanker exerts a 30,000 or nearly 30,000 ton excess buoyant force. Okay, so we'd have to keep this thing tethered. In a grand total, we could do it over more than one tether, but we would need to be able to restrain 30,000 tons. That is, if it was a concrete block, that's something like about a 25 cubic meter or 75 cubic foot block of concrete would weigh 30,000 tons. That's something that we would have to moor a 1,000,000 barrel tanker up with. If we went down to 100,000 barrel tanker, we'd have a 3,000 ton buoyant force. And if we went all the way down to 10K barrel tanker, we would have a 300 ton force. Of course, now the next most important thing to understand here is that the concept, if you're standing on the seafloor and you're looking at sea level, you can actually look at buoyancy as a vector field. Okay, this vector field has one direction, straight up. It can carry not only a million barrels of oil, but 30,000 tons of cargo from 6,000 feet on the ocean floor to sea level. Okay, buoyancy is a vector field, and a bladder tanker is a controllable vessel in a vector field. Of course, now the next calculation and understanding, once you have a vector field, you have a mass times an acceleration times a distance. See, you get it? Yeah. you have a force. It's a vector field. All right. The vector points straight up. No matter where you stand on the ocean floor, the buoyancy vector force points straight up. That's an extraordinarily powerful thing to understand. Now, if you look, the next thing to do would be to calculate entropy. Okay, this is going to be a total of wasted energy in this system. Now, on a 1 million barrel tanker released from 6,000 feet to sea level, there is a 670 megawatt of energy. There's 670 megawatts of energy here. Now, if this is unrestrained, if that is unrestrained, it's gonna matter in figuring out how to, the tensile strengths of material and stuff and the wave motions. That energy will be absorbed by the oil in the ocean around it and heat. Now, 670 megawatts is a lot of energy. Okay. However, I want to point out that that's going to go into like heating oil and stuff. All right. Now, if we go down to 100,000 barrel tanker, we're talking about 67 megawatts. Now, I'm going to explain to you something here about this. Remember, I just told you buoyancy is a vector force. Okay. Now, this is the energy that this system has, that if it's not used in any way or restrained, it's going to be a total amount. The idea here, then it becomes an idea. I point this out because if you look at a nuclear power plant, they talk about the megawatts, like 100 megawatt power plant. That's kind of a heat rating of the core. It's not really an output. If you look at a dam, like Royal Gorge, any dam, they always talk about the megawatts. Okay, they're talking about megawatt thermal energy, like megawatt energy. In a dam, it's a volume of water moving past a point in time, and it can be used for dinner. Hold on now. I'm just telling you here, this is what you're measuring. All right. These balloons, these tankers, since they're in a vector field, they can be measured just like you would measure water running out of a dam, past a point in the dam. Okay. Now I'm going to look here operationally here on the seafloor. Once you have a wellhead, you can actually put a manifold on it and use a pressure regulator. It's incredible when you look at some of these pictures of some of this deep ocean crude production. Some of these pipes are incredible. I mean, I don't know, they're like 15 foot in diameter, and there's looks like maybe a foot or 2 foot of steel thick. These pipelines are massive, and they must be very expensive. If you if you pass the gusher phase, you don't even need a regulator anymore. But what I'm going to tell you though is these balloons, when they are on the seafloor, you could actually use something more like fire hoses to fill these balloons up, because the pressure that you need is only about 50 to 200 pounds. If you were up on the surface, whether you're forcing fluid down or pumping fluid up or pumping fluid, if you tried to pump fluid down through a rigid hose, a rigid pipe, you're doing what they call a vertical lift, okay? Either way, all right? You're still lifting a vertical column of water, okay? If you're pushing down or if you're pushing it up, pumping it up or pumping it down, it takes 2,700 pounds to fill a tanker, to fill one of these tankers, because you're using rigid pipe. When you move, and that's what co-pilot says, moving the oil, the source of oil, the pump, and the thing all together eliminates all those pressures, and all you need is 50 to 200 pounds. The reason why is because when you're not lifting, when everything is at the same level, you're not lifting a column of water. In fact, what happens with a bladder tanker is it expands in all directions. It expands in all directions. It doesn't lift anything up. All right. It's only marginally more pressure than what the ambient pressure is around it, because the bladder expands in all directions. It's also like a battery. It's going to be storing energy. You take a very small amount of energy over a long period of time. You keep filling this thing up. These tankers actually become buoyant at somewhere about 18% fill. The materials and stuff co-pilot calculated out, these tankers he and I are working with become buoyant at about 18%. That's kind of important, okay? Now, let's move on here. I want to make this quick. Just remember, we're trading all those big, heavy steel pipes for a regulated manifold, and if it's not a gusher, we don't even have to really worry about regulating it for fire hoses to fill these tankers up. Look at it. Think about that. If this had ever been thought of before, this would be being done right now. I'm telling you. It's obvious, isn't it? Wait until the end. It'll be real obvious at the end. I mean, these colossal steel pipes versus fire hose. Do the math, people. Oh, and one last point, too, about that LNG. See, it's funny because if you built a train track, you gave it a slight grade, instead of a train, you got to think of it as a train without an engine that's rolling downhill, just freely rolling down a train track. In this case, though, your LNG train would actually be rolling uphill. Are you following me? You could give this a gradual exponential curve. You would have to make a train track, but you could also use smaller tankers too. You could maybe get down to like a 10K bladder tanker. The thing about it is it's all about displacement, right? But anyway, let's get back into the conversations here. One of the things here I wanted to point out too, one of the reasons why, and you're looking at depths of water in the continental shelf up to about 600 feet. I want to talk briefly about this. It's interesting because a 1 million barrel oil tanker would be roughly the size of the Hindenburg. If the airframe, the air bladder on the Hindenburg was an oil tanker, it would actually be about 1.2 million barrels of oil. So how big is that thing? Well, in more familiar size, it's significantly bigger than a battleship, but it wouldn't quite be as big as an aircraft carrier, but it's in that class, okay? This thing is actually a huge frame. It's like 800 feet long and 150 feet diameter, something like that. I don't really remember exactly. But anyway, to do these calculations, we're just using like cubes and spheres. They're roughly the same. So a 1 million barrel tanker would be 54 meters or 220 foot cube, okay? It would also be a 240 foot diameter balloon or a 66 meter diameter balloon. That's big. The reason why that matters is at 240 feet, you got to realize in the continental shelf, to use this thing, you would want to be at 600 feet just to begin with. It's just because it's that big, okay? Now, if you go down, now if the next size down, this 100,000 barrel tanker would be 25 cubic meters, or just about 104 cubic feet. If it was a balloon, a sphere, it'd have 112-foot diameter, or roughly 31 meters. Okay, these are pretty big. I'm not going to mess with the 10K. It's a little bit smaller. I just want to move on. I just want to point out, it's one of the reasons why I say this thing would only be usable in really deep ocean crude. Okay. Now, we've already looked at the excess buoyant force in tons and the power, the entropy calculations. Okay. Now, here's where entropy calculations are going to come to matter, because that's a lot of wasted energy. And the question now becomes is, can we take advantage of some of that wasted energy without it becoming a bunch of tidal forces that are heating the oil and the water up? It's not that big of a deal. You can mitigate a lot of the tensile forces by simply making these tankers a little bit bigger than their capacity anyway. That would transfer a lot more energy into the mixing and warming up of the oil, which might be an advantage to pumping it out of these things anyway. Even that, but actually, what I'm going to call, if we can actually absorb some of that energy, we can use entropy in this vector field in a controllable vessel to generate electricity, actually. And I'm gonna run this one by you first, because it's more than just electricity. But I call this part of this discussion spin me up. Okay, now in this episode, or part of this, I'm going to title this one "Spin Me Up, Scotty." This is in a little bit of honor there. Scotty was on the old Star Trek series. Scotty was the engineer of the Starship Enterprise. Of course, Kirk always was noted saying, "Beam me up, Scotty." In this, I like to honor him a little bit by saying, "Spin me up, Scotty." Now, the whole idea about this is going to be to slow the ascent rate to extract some meaningful work out of that entropy equation in the ascent of this bladder tanker. And it's real easy. We're going to simply tether that bladder tanker to a flywheel. Now, let's start out by talking about mounting a flywheel on the ocean floor, okay? This tether, they do a lot of research. There's a lot of stuff in this research they do with materials research, where they talk about building a tether like for a space elevator out of some really super strong materials. Now, they're actually pretty good at it, but they're talking about making a tether that's, I don't really know, 100 miles long. It's long. It's really super long. I don't know. And using it in space, et cetera, et cetera. But this tether, what we really need is a tether. If we're going to mount the flywheel on the ocean floor, we need a tether that's, say, roughly 5,000 foot. Now, this could be like a real flat band, and the flywheel could be a really kind of a flat band flywheel. But anyway, you fill your balloon up, you fill your tanker up, and when you release it, instead of it just zipping up to the surface, it starts rotating a flywheel. Okay, it starts imparting a lot of that energy to a flywheel. So we're trading some of that entropy as usable work to spin a flywheel on the surface of the ocean. Now, somewhere when that balloon gets close to the surface, it won't have near the energy it had before when it actually surfaces, so it won't be quite as bad. But also, it will completely pull the tether free off of the flywheel. Okay, it'll completely separate off the flywheel. Now, I have various schemes of how you can use carry, and you can do these, how you can spool these tethers, the type of spooling you could use, and the type of ways you could put them to work on a flywheel on the surface. There's a number of different ways of looking at that. I'm not going to go into talking a lot about any of that, but I want to tell you something here about this idea of spinning a flywheel using these balloons to spin a flywheel on the surface of on the ocean floor. Number one, you could use it to make electricity on the ocean floor, which is going to become important later on. You could also use it, like when you get it spinning, if you wanted to do this flywheel deal, you want to bring it to a stop. Well, you could do some hydraulic braking, which could actually bring this flywheel to a stop so it could be reloaded, so it could be retethered for the next balloon. But the thing about it is, in this hydraulic braking here, that would heat water. You know, you could, I would create a hydraulic brake that would heat water. And then you could also use that same flywheel when it's braking and heating water to pump that heated water down into the oil reservoir to heat the oil up and to help heat the oil up, see. So you could recover some of the entropy on the surface of the ocean with a flywheel. Now, this is completely doable. I want to point out that you know, this technology of these tethers, you know, and this space elevator, these types of materials, these synthetic materials would be an ideal choice, and this could easily be done. But I'm going to demonstrate something to you in this controllable vector force that you really don't have to actually even put the flywheel on the floor of the ocean. Sometimes you might want to, but in this spin me up, Scotty idea, you can actually put a flywheel on your platform, even a floating platform. Okay. Now, the thing is you're going to need a tether that's much longer. It's going to have to be like, instead of a mile long, it's going to have to be a little, like, say 2 miles, because you're going to run it down from the flywheel across some pulleys and over to your bladder tanker. When your bladder tanker gets full, and remember, we're filling it up with a fire hose, not a big steel pipe. Once it gets full and our battery's kind of stored up with that oil, and we release this buoyant force in this vector field, when it starts pulling up, when it starts moving up in the vector field, it can actually spin a flywheel on a platform, as long as we have that flywheel connected through a pulley. So we need about 2 mile tether. All right. At the time when the tanker hits the surface, the tether around the flywheel will have come off of the flywheel, and the flywheel will simply be free spinning after that. See. All right. Now you could use that same by using like a clutch mechanism. Now, while that flywheel's spinning, you can actually take the spool off of the flywheel and wind that tether up again and draw that balloon back down to the ocean floor so it could be refilled. The interesting thing about using that generator or the flywheel on your platform is that allows you to makes it real easy to control the tether, because it's sitting up on top. It's twice the tether length, but it is above the ocean here. It is above sea level. So it's much easier to spool the tether and to clutch it into the flywheel. Now, you can do the same type of thing if you're on the seafloor. My idea is that thing would spin off of one spool. All right. Now, that spool that would be on the flywheel would be decoupled and be part of a cargo that would be brought up by the next balloon going up. In other words, the tether and the spool would be reused. We would take the spool off of the previous balloon, put it as part of the cargo hold of the tethered balloon. All right. The tethered balloon, it will have a full spool that will have been re-spooled up on the service vessel on top. They will spool that. They would have spooled this up. Then that balloon, when it comes down, the pre-spooled spool would be clutched into the flywheel. Now, the flywheel could actually be brought to a complete stop through hydraulic braking and heating and all the other nice things you want to do with it. All right. By doing, you would have half the tether length, but then you will have to carry a spool along with you. Okay. That would be one way to do it off of the sea floor. Now, by putting your flywheel on the platform and the tanker, that's all. The tanker's always going to be filled up at the same point on the ocean floor either way, see? Now, you simply run your fire hose size pipes to fill these balloons up, and you can run them for miles. You can run these fire hose size pipes for miles to fill these tankers up. You don't need these big steel pipes along the seafloor, and you don't need these rigid pipe platforms anymore. All that's gone, and you're generating electrical power now. It's kind of funny because while you're tankering, it's like a ship or a boat that flows down a river. All right, but instead of flowing down a river, it flows up a river, and it pulls on a string that generates electrical power while it does it. It's amazing. And when you're looking at these, at 67 megawatt entropy of 100,000 barrel tanker, it's only a 3,000 ton pull. It's only a 3,000 ton more. And if you're using pulleys, that gives you about 1,500 ton pull on a flywheel. You can generate some power. You can control the ascent of this tanker and generate electrical power. It's kind of like a different kind of windmill. It's kind of like a windmill out in the ocean, but it's not a windmill at all. It's simply a controlled vessel in a vector field. Now, all right, now that we've covered electrical power generation, I'm going to move into the other point of all of this. And this is, when I get into this, you're going to see why I say I don't think this bladder tanker idea has ever really been thought of and or really ever been done before. I'm going to show you something now about what I'm going to call that deep ocean DOTC, the Deep Ocean Transportation Corporation, can do for you. Watch this. Okay, now I'm going to get into what I call the grand finale. We're going to be looking at things like deep ocean mining and deep ocean exploration. It's kind of interesting. Let me just point out, the Earth's roughly 75% water, ocean. Now, a lot of meteors actually fall to the Earth, and I suspect that there are probably a lot of meteors that have fallen to the Earth and are actually maybe somewhat, if they hit out in the ocean, and 75% of them on average will have, there might be some meteors out there that may be in relatively good, intact, and or a small debris field. Now, one of the things about these tankers is you can actually run a fire hose off of a wellhead, however far, 100 miles, 200 miles from a wellhead, and establish a bladder tanker that can lift, 3,000 tons to the surface for you. Now, if you have a bladder tanker with a gondola and a ballast in it, instead of spinning a flywheel, you can actually control the height getting this up. The amazing thing is, if you keep the pump in your oil reservoir and this bladder tanker at roughly the same depth, there's no real pressure involved in filling that bladder tanker balloon up because it expands in all directions. Keep that in mind. Now, I just point out that if you can actually, using this, if you want to, you can actually take robotic exploration equipment down to the floor of the ocean and run around with it and put it on a balloon, bring it back up and charge batteries. You can do all kinds of things. All you got to do is go see your local oil producer and rent a fire hose line from him to your bladder tanker, 100 miles away, 200 miles away. It's amazing what you can do with this hydraulic vector field in a controllable vessel. You can use it for mining. You can use it for exploration. I mean, think about some of these meteors. If you ever found one out there, some of these meteors have a lot of very valuable materials. Speaking about valuable materials in mining, I'm going to take you down here even deeper than you've been before. I'm going to take you down to that 10,000 foot limit that Copilot says these tankers will operate at. Now I want to show you something. We have, let's just say we have an oil wellhead and it's sitting at 6,000 feet. That oil reservoir that it's actually pumping oil up out of is actually typically 10 to 20,000 feet, because it's not just the surface. It's 6,000 foot to the surface, but typically there's another several thousand feet they have to drill to get into the oil reservoir. That's kind of important, because I want you to keep in mind as we move on that the oil we're actually pumping out of is actually even deeper than where we're taking than where we're going to be using it. This is actually creates what you might call a siphon. See, you actually not only do you not have to pump, but you can actually siphon. You can actually siphon oil out. See, if you get the right depth. But that doesn't really matter, because one way or the other, you're just going to be running. You could be running a fire hose 500 miles from an oil wellhead 500 miles away at 6,000 feet. But here's where deep ocean mining starts coming in this concept of the Deep Ocean Transportation Corporation Incorporated. Anyway, here you go. They have this stuff. There's these rare earths, or what they call, there's these nodules, and they're all over the place out here. And these are ultra deep water. These nodules start forming somewhere around 12,000 feet depth. Okay, that's important, because we have a tanker balloon here. We have a controllable vessel and a controllable vector field sitting at 10,000 feet. We can spin up a flywheel, or we can load up a gondola, transport equipment up and down to that depth. Now, these nodules, these rare earth nodules, they're between 12 and 20,000 feet, and they're apparently all over the place. They're very valuable and highly sought after. Up to now, there's not been any real viable way of doing anything. Here, this is why I say this idea is never, these bladder tankers have never really been explored, because here is something big for you. You can actually set yourself up a base down here. Now, you're going to have electricity. You can do it one of two ways. You can spin flywheels, or you can fill balloons up. You can move equipment back and forth, so you can take batteries up and down. You can use these oil tanker bladders in a real slow, controllable way to move batteries up and down to the surface where they could be charged, and sent down. And you could actually put some wings on a deal here. You could actually make something like a bird, like a spiraling bird, that brings this stuff back down to the surface in a real controllable way. You could kind of make it almost like a plane, but not so much of the bladder tanker. It's just a glide vehicle to get it back down to the surface. It could carry charged batteries. It can bring down mining equipment, things like remote operated mining equipment, scrapers and things. So here's the nutshell. I'm getting real tired. My voice is getting raspy. You can use this electric robotic mining equipment, and you can mine these nodules. Now, all you're doing is moving stuff from roughly 12,000 to 20,000 feet up to a point about 10,000 feet. You got a source of electricity. You got battery vehicles who can probably cover that distance. You could even make a big truck type thing that was a big battery that could be driven out to a remote location and charge up many of these other smaller robots while they mine, get loaded back up and drive back, and get simply put on a gondola and taken to the surface and have the battery charged there and all the mining's recovered at the surface, moved on ship or whatever. See, you could also, if you have a generator down there, a flywheel, you could be spinning the flywheel up and generating electrical power that could be charging one of these big truck batteries. So by using these bladder tankers, it's incredible because it's like putting all your minings on a barge that's going down a river. It doesn't cost you nothing. As a matter of fact, the amount of oil that you're bringing up along with you helps pay for what you bought from the oil company in the first place. Do you see how positive all of the economics of this is? But one of the greatest economic promises of all of this is just how powerful this is for the creation of jobs. Look at all of these jobs, making all of this mining equipment, making these bladder tankers, making these fire hoses. We completely change the way we do deep ocean crude and ultra deep ocean crude with this. The fact that we do not have bladder tankers lifting 3,000 tons of nodules from 10,000 feet up to a processor tells me that this idea has just never been thought of before. It's amazing. Co-pilot complimented me as an engineer. I kind of think of myself more as a physicist. I don't know. It's just kind of funny because I don't really do this kind of work, but this, if it had been thought of before, we'd be doing it now. This is what I say, welcome to the future. Welcome to the future. This is where your jobs, this is what people are going to be doing in the future. This is an incredible period of time. And I also like to say one thing. I'm going to end this with one thing. I am a major, major, major supporter of President Donald J. Trump. I personally would like to see this president do a third term. He is a gift from the heavens. God bless America, and God bless President Donald J. Trump.